with the next one. This is the second module that we're going to do, and we're going to close this one down.
Hey, George, while you're doing that, got another question for you from Bing. How do we know 238 uranium did not decay before 4.5 billion years ago? Does it not exist?
Tell you what, Kurt, why don't you take that one, and I'm going to make sure I can get the right module pulled up here.
I'll give it my best, George.
Sorry, I had these all pulled up beforehand. All right, I am ready to go here on module number 2. Let's go full screen. Okay, everybody ready to jump in with number 2? This one will go a little bit faster. We had a lot of material to cover in number 1. We had good news and we had some bad news. Now we're going to talk a little bit about just the methods. This is pretty straightforward. Everybody happy? All right, so we're going to talk about how you actually determine the uranium lead and lead ages that we're interested in. And recall that we have one of each. We want to measure this ratio, 206-238. You measure the ratio, you calculate the age out here. And then we measure 206-207. And the slope of that line is the 6-7 line. Those two intersect at that point. So your analysis is right here. If you're lucky, right on Concordia. You know the age is 2.9 billion years old. Good news. Okay, it turns out of these two systems, you measure them actually in somewhat different ways. It turns out that measuring the isotopes of lead, 206 to 207, for a mass spectrometer, that's actually kind of easy. Mass spectrometers can do this quite well, and that's because lead 206 and lead 207 behave quite similarly in the plasma as they go through the mass spectrometer, as they're separated in the analyzer. 6 and 7 behave pretty similar, and that's because they're the same element, right? They have the same charge and size and all that. So just a slight difference in mass. So the measured value off the mass spectrometer, 206, 207, is very close to the true ratio. You might have to do a correction of 0.1% or 1/3%. We call this the mass bias correction. So we will do that correction. The bad news is that 206 lead and 238 uranium actually behave very differently in a mass spectrometer. As the laser is pulsing down onto the sample surface, as that material is coming out, as it goes through the torch into the analyzer, 206 behaves very differently from 238. Very different size, very different charge. And so you actually get significant fractionation of 206 to 238. The ratio that you measure with your mass spectrometer, you're going to be off by like 5% or 10%. That's really bad news, right? You spend millions of dollars, maybe $4 million on an ion probe. You do an analysis. Oh, sorry, your analyses are 5% or 10% off. That's just the way it is with mass spectrometers. They never tell you the correct isotope ratio. In every case, you have to do a correction to get to that true isotope ratio. So let's talk about how we do this. There are two ways you can do it. One is called isotope dilution. And when we do that, it's in a solution form. And so we put that solution into a TIMS, a thermal ionization mass spectrometer. We have to dissolve the crystals that we're going to analyze. We have to add the spike of this material. That's how we're going to dilute the isotopes. You have to chemically purify that material, and then you calibrate it by comparison with a spike. For ion probes and laser ablation systems, we do this by standard sample bracketing, and that's because we're not going to dissolve our sample. We want to leave our sample crystal in situ as a solid material, so we can't add other isotopes to that. So what we're going to do is we're going to ablate out material or sputter the material out of the crystal. We're going to measure the isotope ratios that come off, and then we're going to calibrate by comparison with some kind of a standard. That's how we refer to this as standard sample bracketing. And the standards that we use, this is a really challenging aspect of doing this type of calibration. So just to kind of take you through a little bit of the details, I'm not going to work through everything on the left here, but the diagram shows actually in a very simple way how this isotope dilution thing works for ID TIMs. So here's our isotope spectrum 238, 235. This is what we want to know. 208, 207, 206. This is what we want to know. And now I've used red for radiogenic and blue for initial. And then what we do is we dissolve the crystal. So we get out all of the uranium, all of the lead isotopes. And then into that with a pipetter, we add a little bit of a solution spike. And that spike is cool. It consists of 233, which is not naturally occurring. It's uranium, but it's an isotope that does not occur in nature. And also lead 205, also not naturally occurring. So all of the 205 and all of the 233 that we measure in that solution comes from the spike. All of the 6, 7, 8, 5, and 8 that we measure from the solution comes from the sample. And so in our mass spectrometer, we can do what mass specs are really good at. We can measure the 233-238 ratio. We can measure the 205-206 ratio. If you know how much 205 you put in, how much 233 you put in, then just from that ratio, you can calculate how much 206 is there and how much 238 is there. And then off you go. So this is how we calibrate the ratio for 206, 238 that comes off the mass spec, which is incorrect. We do the correction based on the spike, which we know the isotope composition of. So this is what we call isotope dilution, thermal ionization mass spectrometry. And people can do this with amazing precision. You can do this such that you get a 206, 238 age down to 0.1% or even less than that. This is a very time-intensive technique to do. This is the mass spectrometer that we use. To do this, you have to work in a very, very clean lab because you're dealing with very, very small amounts of lead and uranium. You want to make sure that you don't contaminate that solution with environmental lead. So you do this in a clean lab that's all Teflon. You wouldn't be able to do this without Teflon. You wear a bunny suit. You can't put gas in your car on the way to work in the morning because gas still has too much lead in it. You would contaminate your sample. So this has to be done in a very clean environment. It's very painstaking. It takes about an hour to do each analysis. That's pretty expensive to do it at that rate. So you might pay $100 or $200 for an analysis. But the good news is you get amazing accuracy, 0.1% accuracy now from ID TIMs. So if you're doing high precision geochron, this is what you want to do. Second technique that people do, this has been around for a long time now, is ion probe. You can refer to this as secondary ionization mass spectrometry or super high resolution ion microprobe analyses. And this is done differently. Along with your unknown zircons, the zircons you're interested in, you also mount some standard zircons, and these are zircons that we know the age of. So we know the 206-238 ratio of those crystals. You measure the 6-8 ratio on your mass spectrometer that day, actually during the analysis of your unknowns, and you determine the fractionation factor, 5%, 6%. You have to change the ratio that's measured by 6% to get to the true age. And then you assume that your unknown crystals are going to have that same fractionation, and you apply that same fractionation factor to correct for 6-8 that you measure for your unknowns. And then when you do that, you can calculate the age. So we call this standard sample bracketing. We usually do 5 unknown crystals. So 5 of these, 1 of those, 5 of these, 1 of those. Takes a little bit of extra time, but that's how we do the calibration. This allows us to get ages that are maybe 1% or 2%. There's no way we can get to 0.1% doing it this way. If you ever get a chance to go to an ion probe lab, you should take the advantage to do that. They are super cool instruments. This is one that's the shrimp version of an ion probe. This is the Kamika version of the ion probe at Wisconsin lab. These are monster machines. They're hard to keep going, constant tuning to keep them working just right, but they're just amazing instruments. And they give you spatial resolution, at least in the depth downward, that's almost kind of atomic layer by atomic layer. So in complicated zircons, you can really pick apart that zonation of a crystal really well with an ion probe. This is kind of the power of ion probes, is that spatial resolution. Turns out laser ablation ICP-MS works exactly the same. We have the same standards, the same unknowns. We do standard sample bracketing. The precision that we get is about the same, also 1 to 2%, something like that. And so here's the instrument that we use. This is still basically two different instruments. There's the laser on one side and the mass spectrometer over here. And the connection between the two is this tiny little Tygon tube. The instruments, they talk together, talk to each other a little bit, but it's still amazing in this world today. After 20 years of doing this routinely, you buy a laser, you buy a mass spectrometer, and you're the one that has to figure out how to get those two to work together and talk to each other. They're not made by the same company. So the sample is analyzed in the laser beam pulses down onto the sample surface. Where you're hitting that material, it's carried in helium gas. It goes through the tube into the mass spectrometer, enters the mass spectrometer here. This is actually an amazing thing about these mass spectrometers is they have a hole on the end of it. It's about a 1 millimeter diameter hole. And the ionized material comes through the plasma here at the temperature of the sun, high ionization, enters the mass spec here, goes down the flight tube. This is a double focusing instrument. And this is a multi-collector instrument where we have lots of different detectors for all the different isotopes of interest. So with this instrument, this is probably the best instrument to use for uranium lead geochronology. You can measure 238, 232, 8, 7, 6, 4, and 2 all at the same time. And I'll show you a curve that shows that here in just a minute. And you can also do other isotope systems. This is how we use hafnium isotopes, which can only be done on a multi-collector mass spectrometer. So here's how it works. This would be an analysis with a multi-collector instrument. The laser is off. For about 15 seconds, you're counting on backgrounds. And you can see you actually have a fair amount of background material. All of these lead, mercury, uranium, thorium, there's a little bit of that material present in the backgrounds for every measurement. And you have to subtract that material from your peaks to be able to get the true measured value. So this is actually one of the sort of challenging aspects of laser ablation ICP-MS, is to try to get these backgrounds down as low as possible. So then you fire the laser right here. We might fire the laser for about 15 seconds. See lots of 238, a little bit less 232. You see some lead, 206, 207, 208. You see some 204 down here in purple. You see some mercury. This is the challenge. There's mercury 202 and 204. What you also see on here is that the intensity decreases as you're drilling down into the zircon. The intensity comes down a little bit. And also kind of, you can probably see this, the change in intensity for uranium is actually a little different than it is for lead. Lead and uranium behave differently as they come out of the laser pit and go into the mass spectrometer. So we're going to have to do another correction for that. Here's how we do these corrections. This would be during that 15 seconds of analysis. You start at time 0 here. You just fire the laser, 1 second, 2 seconds, 3 seconds. And what we see is that the 6-8 ratio comes up. It starts with a lower value, kind of a curve to the pattern. And then eventually, as you're drilling down into the zircon crystal, you get this flat segment here. This is the change in ratio between 206 and 238 as you're going downhole. So one of the things we need to correct for is the downhole correction, the fact that 6 and 8 fractionate differently as you go deeper into the pit. And then here's this 5% or 10%. Every measure isotope ratio you measure is off by 5% or so. And so you have to do that fractionation correction. So this all happens in the software package that you're using. Kurt is going to show you this in great detail later on today. When you do the hands-on activity, you're going to analyze this fractionation pattern and look at some of the challenges of doing that. Here's the good news. Like I said, mass spectrometers are really good at measuring 206, 207 because they're both lead. They behave similarly. And so the true age is actually very similar to the measured age. You might be only off by 0.1%. You would still do a very small correction here, but this is a minor mass bias correction. And you generally do not get a downhole fractionation because 6 and 7 are behaving similarly as you drill down into that zircon crystal. When you analyze the data, you'll see this in the software that Kurt is going to be working with you on later today. we take the uncertainties of these measurements and we divide them up into two different types. This is really important that you understand how this works, because this is going to go into your report. When you report the ages, it's going to go into your data table. And so there are some measurements that just depend on a single analysis. They would be the ratios that you measure, 6'8", 6'7", 6'4". We don't measure 235, right? Because you don't need to. And those are propagated through the age equation, and those might end up giving you a 1% or 2% uncertainty at 1 sigma. Then there are other analyses, other uncertainties, sorry, that come into each analysis. And these would change the whole data set. So the easiest one to imagine for that is the decay constant. What if our decay constant is 0.1% off? Well, then every age that you calculate is going to be that same 0.1% off, right? We call that a systematic error or an external error. Blanket on all of your analyses, they all go up and down together, whereas the internal or random, those uncertainties are independent for each analysis. If you add up all these different uncertainties, maybe your standard is off. Maybe it's not exactly the age you think it is. Maybe your common lead composition is not quite right. Your fractionation factor is not quite right. All of those external uncertainties might add another 1%. This is one of the challenges in reporting data, is to know how to do this. How do you report your data? Just with these or together with those as well? And there is a methods paper that we'll talk about later from 2016 that kind of describes how you do this. Getting toward the end here, here's just a comparison of these techniques. And fortunately, we're in a world right now where I think most geochronologists would say that each of these individual techniques has a really powerful aspect and maybe an aspect that's kind of a weakness. And so to kind of emphasize that, for ID-TIMS, it's kind of slow, it's kind of expensive, but man, is it precise. 0.1% precision and accuracy. You can't do any better than this with any isotope system. So this is the best you can do in terms of precision, but it's going to take a lot of time and it's expensive. For ion probes, you do 4 analyses a little faster. You get about 1 to 2% accuracy, but this has amazing spatial resolution. If you have a really complicated crystal, this is the best technique. You can analyze it atomic layer by atomic layer, really pick that crystal apart. And then for analyses where N is important, the larger number of analyses are essential. Laser ablation ICP-MS is the way to do this. The cost has gone way down. My whole career, I've wanted to try to be able to do an analysis for $1. That's been our kind of challenge. We're finally there, that it takes $1 to do an analysis. That's great. It's 1 to 2% accuracy. We don't have the same spatial resolution as an ion probe. Can't quite get that degree of resolution, but this is powerful for techniques that require that high efficiency. So here's kind of how we see the world. Depending on what you want to learn from your sample, these are the different methods that you can apply, and hopefully you know enough about them now that you can make those decisions. So here are the best practices from the methods part. First, you need to figure out which is the best instrument or the best method to use. You want to go and work with a lab that has a methods paper where they describe how they do all of the analyses and the data reduction. They have to have a data management plan. NSF requires this. This is part of every proposal that you put into NSF. Make sure you acquire CL images and you use those to pick your spots. Definitely visit the lab to generate your data. You're going to learn so much by being there, operating the instruments, just seeing how the data are acquired, actually collecting the data that you're going to report, and of course, ask a lot of questions while you're there. If you can, try to generate that final data table and the figures before you leave the lab. And that's just because you are fully engaged in the process. The people in the lab are right there with you. If there's any issues, you can work on them right then and there. If you come back to the lab a month or 2 later, it might be hard to reconstruct exactly what was going on during your session. So this is kind of a best practice. Have the lab provide this metadata table. This is what's going to go into your publication. It just talks about the methods used. And then have the lab folks check your results and interpretations before you go to print. So this is kind of how we operate. A lot of labs in the US and around the world operate exactly the same way. This is not just our lab, but a lot of people, I think, have kind of migrated toward these best practices. So I'm going to stop there. That was the end of module number 2. And I'll see if there's, and we'll take a 5-minute break here and see if there's any questions about module number 2.